Hello, students. So, at this point in the class, we've finally stated all three of the properties that define the real numbers. The real numbers are a field, which is ordered and complete. And maybe just the field axioms are straightforward enough. They're just what properties should multiplication, division, addition, and subtraction have. There should be a sense of inequality that plays well with the properties of addition, multiplication, subtraction, division. And then completeness. The real should be complete. And what does complete mean? Well, an ordered field is called complete if every set, which is non-empty and bounded above, has a supremum. And remember, the supremum is, if you like, a least upper bound. So every set that's non-empty and bounded above should have an upper bound which is smaller than every other upper bound. So with that in mind, the first kind of difficult thing we did with the Archemedean properties was we proved something that wasn't terribly surprising. We proved something that you all know and love. You know that the natural numbers are an unbounded subset of the real numbers. No matter how big a real number you say, you should be able to come up with a natural number that's bigger than it. So let's try to prove that. And here's how the proof will go. It'll be a proof by contradiction, and it'll be a really interesting proof by contradiction. So let's suppose that the natural numbers are in fact bounded above. Well, let's see, the natural numbers are non-empty, right? 1 is a natural number. So by completeness, the natural numbers will have a supremum. Let's call that supremum S. S is a good name for a supremum. So here's the game. We'll try to get a contradiction by thinking about this S and proving that that S is not the supremum. So here's how the game will go. So first question, S minus 1, is that an upper bound? Well, no, it's not, right? Why is it not an upper bound? Well, if S minus 1 were, and I'm going to use the abbreviation upper bound, then as S minus 1 is less than S, S would not have been the supremum. So what does that mean? That means that S minus 1 is not an upper bound. Well, what does that mean? S minus 1 is not an upper bound. So what does it mean to be an upper bound? To be an upper bound means, so let's think about it this way. Let's try to decide what S minus 1 is an upper bound would mean for all natural numbers. N is less than or equal to S minus 1. But in fact, we know that that's not true. Sorry, this is just scratch work to figure out what the logical calculus should work out to be. So let's just negate this statement. So when you negate a universal, you'll get an existential. So there should exist some natural number such that this is not true. If a universal statement is not true, then there must exist a counterexample. So there must exist something where this does not happen, i.e. a natural number where n is greater than S minus 1. So, having done that, since S minus 1 is not an upper bound for n, there exists some natural number n such that little n, as we just saw, is bigger than S minus 1. Adding 1 to both sides, n plus 1 is bigger than S. Well, wait. N is a natural number, 1 is a natural number. The natural numbers are closed under addition. N is closed under addition. So n plus 1 is in the natural numbers. But hey, wait. this is a natural number. That's supposed to be the supremum. But that means that s isn't even an upper bound on the set of natural numbers. There's a natural number what's bigger than s. So that contradicts the fact that s was defined to be the supremum and in fact an upper bound. So what do we conclude? We conclude that the thing that we assumed it to begin with must be false. So, as what have we shown? We've shown that the supremum of n does not exist. N is not bounded above. And I think that's really one of the first cool applications of the supremum that you can cook up. Right? By knowing for the sake of completeness that if the natural numbers had an upper bound, then they would have a least upper bound. You can get a contradiction. And in fact, this statement really is the best you need completeness for this to be true. There exists ordered fields, and you know that the natural numbers embed into every ordered field, where the natural numbers have an upper bound. And I'll leave it to you to puzzle on that. So let's keep things moving. So the integers, the natural numbers, aren't bounded above. The integers are given by the natural numbers together with 0, together with the additive inverses of all the natural numbers. Here's a claim. This is not bounded above and is not bounded below. Let's proceed by contradiction. I mean, if it's not bounded above and it's not bounded below, and we want to proceed by contradiction, let's suppose it's bounded above. Later on, we'll assume it's bounded below. So let's suppose the sucker is bounded above. Let's let u be an upper bound. Well, wait. The natural numbers are a subset of z. That should mean that u is an upper bound for the natural numbers. That should contradict theorem 2. So let's just take a moment and verify that claim. And apparently this is just to demo how to show something's an upper bound. So how do you show something's an upper bound? You need to show that everything in the set is less than or equal to it. So let's consider any n in the natural numbers. So let's see. Unions only make things bigger. So the natural numbers are a subset of z. Z is a union of things. This number n is in z. So since u is an upper bound on z, n is less than or equal to u, proving that u is an upper bound on n. Sorry, there's a poorly placed cable. Which is a contradiction. The exact same reason gives that z is not bounded below. Indeed, if L is a lower bound, then I think I won't. You should take a moment and explain why minus L will be an upper bound on n. And maybe I'll even give you a start. Consider any little n in the natural numbers. Then, actually, shoot, let's just do it. Well, then, by the definition of the integers, negative n is in this set, which is a subset of z. So negative n is an element of z. So negative n is bigger than or equal to L, as L is a lower bound on z by assumption. Well, but let's take a look at that. Then you can multiply both sides of this by -1, and that'll flip the inequality. N is less than or equal to negative L. And so negative L is an upper bound on n. Again, this gives the exact same contradiction. So that means that the integer z can't be bounded above, and can't be bounded below. And that completes the proof. Cool. So all of these do appear as results in class, but some of them got involved. So I figured it would be nice to have a version of this same note packet that can be gone through at any speed you like. So let's just keep on going. So here's the next of the Archimedean properties. If a and b are real numbers, and a is a positive real number, then there's some natural number n such that a times n is equal to b. If you like, what this says is no matter what two real numbers you pick, as long as, well, that one's positive, then I can multiply it by a big enough natural number to make it bigger than any other number you like. Well, let's prove it. Well, consider a and b in the real numbers. And, well, let's stick all the assumptions there. Let's assume 0 is less than a. So there will be two cases. And by the trichotomy law, really there are three cases. Either b is less than 0, or b is equal to 0. So b is less than or equal to 0. Or b is bigger than 0. 0 is less than b. So let's deal with this first case first. Let's assume b is less than or equal to 0, and let's take n to be equal to 1, and let's just check that inequality. Then a times n is a times 1. Hey, that's a, which is bigger than 0 by assumption. But notice we also assume that b is less than or equal to 0. So since a is bigger than 0 is bigger than or equal to b, not the trichotomy, the transitivity law, says a is bigger than b. So n times a, n is 1, is bigger than b as claimed. Everyone cool? I don't know why I ask. You can't answer. There should be a space there. So on the other hand, let's deal with the case that's actually interesting. Let's assume that b is bigger than 0. For the sake of contradiction, let's assume that for every natural number n, a times n, we want to show that a times n is bigger than b. So let's assume that for all natural numbers n, a times n is less than or equal to b. We can multiply both sides by a inverse, which is positive. Multiplying by an inequality by a positive number preserves the inequality. We see that for all n in n is less than or equal to b a inverse, or if you prefer, b over a. Right, those two mean the same thing. Aha! But we've just shown that for every natural number n, this is a thing that's bigger than n. So that means that b over a is an upper bound on the set of natural numbers. That contradicts the first version of the Archimedean property, which says that the natural numbers admit no upper bound. So there's the contradiction. And so there must be some n in n with a times n bigger than b. Cool. So this is another one that we did in class, and it's not so hard, but let's do it anyway. So here's another thing that you can conceivably call the Archimedean property. Realistically, the things that are actually called the Archimedean property are the first thing that I call the Archimedean property, the unboundedness of the natural numbers. This result, that you can multiply by a natural number big enough to make any positive number bigger than anything you like. And this last one, well, it's really mostly just stated as the density of Q. But let's prove this corollary 5 anyhow. So, corollary 5. The infimum of the set of things that look like 1, 1/2, 1/3, 1/4, 1/5, and so on, in general, everything that looks like n inverse where n is a natural number, the infimum of that set is 0. So maybe if you don't remember, the infimum is the greatest lower bound. There's another statement, though. L equals infimum of some set, I'll call it star, means, well, if L is the greatest lower bound, L had better be a lower bound. And secondly, for every positive number epsilon, there exists something in this set such that, well, the idea is that L plus epsilon is bigger than L, so it can't also be a lower bound. So L plus epsilon can't be a lower bound, so it can't be less than everything in the set. So let's go through and do it. So first, let's show that 0 is an upper bound on this set. So how do you show something is an upper bound? Well, let's consider, so we want to show that the infimum is 0, right? So we need to show that 0 satisfies these two conditions. Consider any n inverse with n in n. Well, that means, not that means, since the natural numbers only contain positive things, 0 is less than n. So, since 0 is bigger than n, what can you do? You can multiply everything in sight by n inverse. No, that's not the proof that I want to do. Let's prove it this way. Let's suppose n inverse. I want to show that it's a lower bound. So let's suppose that n inverse is less than 0. Well, then that would mean n times n inverse, well, that's 1, is less than n times 0. Hey, that's still 0. So 1 is less than 0, a contradiction. So we assumed that n inverse is less than 0 and got a contradiction. So it must be that n inverse is bigger than 0. Everything in the set looks like n inverse. That implies that it's an upper bound. So, secondly, we showed that if epsilon is bigger than 0, then epsilon is not a lower bound. And we'll proceed by contradiction again. So let's suppose some epsilon bigger than 0 is a lower bound, which would, of course, imply that 0 is not the greatest lower bound because there would be a bigger one. Suppose this epsilon is a lower bound. What would that mean? That would mean for all n, well, n inverse is a thing in this set. N inverse is greater than epsilon. Hey, but that implies epsilon inverse is bigger than n. So epsilon inverse is an upper bound on n, but hey, that's a contradiction. Contradicting the thing which in this particular document is called theorem 2. Cool. So we've shown that 0 is a lower bound, and if L is any other lower bound, then L has to be less than or equal to 0. Think about this and take the contraposition of that statement. That's exactly the definition of the infimum. So we're done. Last step, let's prove the fanciest thing we can using these ideas. Let's prove the density of the rational numbers. Let's prove that Q is dense in the real numbers. So let's prove that for any real numbers, x and y with x less than y, there are some natural numbers m and n with x less than m over n less than y, less than or equal to. It could be less than. We'll prove less than or equal to. All right, well, let's do it. So let's consider any x and y at R and assume x is less than y, as we must. We have to construct some m and n with n not equal to 0, n bigger than 0, and x less than m over n less than y. Let's match the symbols. That's what we need to show. Well, let's see. Since x minus y since x is less than y by assumption, that means that y minus x is bigger than 0, is positive. By corollary 5, 0 is the infimum of the set of inverses to natural numbers. Since x minus y is bigger than 0, could it possibly be a lower bound on this set? Well, no, it couldn't, right? Right, it's bigger than the least, it's bigger than the greatest lower bound, so it can't possibly be a lower bound itself. So if you negate the definition of what it means to be a lower bound, what do we see? We see that there exists something in this set so there's a description of something in the set so that this is less than y minus x. We happy? Good. All right, so this is just specifying that n should be that previous number. So you found a natural number n so that y minus x is bigger than, less than 1 over n. Keep it straight, Chris. Sorry, I get confused with inequalities sometimes. Today's going to be one of those days. So in turn, that implies, let's take this and just add x to both sides. That implies y is bigger than x plus 1 over n. Cool. So what do we have right now? We have that y is bigger than x, and y is bigger than x plus 1 over n for this particular natural number n. If we multiply everything in sight by this natural number n, which is bigger than 0, we'll see that ny is bigger than nx plus 1. And so ny minus 1 is bigger than nx. And I'm going to label that with a 1 whenever I say 1 later on. It'll refer to that inequality. So let's think about this. So if we could find some integer m where nx is less than m is less than y, then we can divide everything in sight by n and get what we need. So let's try to figure out how to do that. So here's how we'll do it. We want to find some m which is less than or equal to ny. So let's let A be the set of all things where m is less than ny. Well, so let's try to figure that out. And importantly, that's integers. Right? We're allowing m to be an integer. According to corollary 3, ny is or is not a lower bound on z. So take a moment to read corollary 3. What does corollary 3 say? It says that the integers have no lower bounds. So in particular, this is not a lower bound on z, as z has no lower bounds. Negating the definition of what it means to be a lower bound, that means that there must be something in z where m is less than ny. Aha. Then m is in A, so A is not empty. So that might seem like something random that it's not clear why it matters. But let's take a look at that set A. It looks like by its very definition, ny should be an upper bound. It's not empty. We found something in it. It has a supremum. So by the very definition of the set, everything in the set A is less than ny. So that means that n times y is an upper bound on A. So by completeness, there's a supremum of A. Let's call it S. So let's pick a positive number, epsilon equal to 1. The formulation of the supremum in terms of epsilons, which was referenced in terms of the infimum on the previous page, there must be some m in the natural numbers such that s minus 1 is less than m. But that means that s is less than m plus 1. Could m plus 1 possibly be in the set A? Well, no, it couldn't be. Nope. M plus 1 is bigger than s, and s is an upper bound on A, since it's the supremum. Thus, it must be that m plus 1 is not in A. M plus 1 is certainly an integer, though. M is an integer, so is m plus 1. It's not in the set, so this inequality must not hold for m plus 1. So it must be that m plus 1 is bigger than or equal to ny. Right? The opposite of that should hold. That means that m is bigger than or equal to ny. There's another inequality that I'll want to use. So here's what we'll do. We'll use the fact that m is in A. We'll use claim 1, and we'll use claim 2 to prove the thing we need, that nx is less than m is less than ny. And that's enough moving parts that I certainly need to use some separate sheets of scratch paper to suss that out. You should do the same. So let's just do some quick scratch walk. Here are the things we know. We know ny minus 1 is bigger than nx. That's the thing that's called 1. The thing that's called 2, we know that m is bigger than or equal to ny minus 1. And 3, since m is in A, we know that m is less than ny. Our goal is nx less than m less than ny. And as with a lot of things, like some things just seem really obvious now. Well, 3 straight up just says m is less than ny. Great. So, awesome, that's good. Now we need nx to be less than m. Let's see. Nx is certainly less than ny minus 1, and this is just scratch work right now, so that's inequality labeled 1. Ny minus 1 is less than or equal to m by 2. Cool, so that gives us everything. So now, maybe what I'll do is, no, there's no way to do it. All right, if I learned anything about editing videos, I'd be able to fix this, but I refuse to do so. So let's just think about what things we just did. So the item that was called 3, well, that was basically that inequality. So let's see, as m is in A by assumption, m is less than ny. Great. By 2, nope, let's do 1 first. Nx is less than ny minus 1 by 2, and y minus 1 is less than or equal to m, So by transitivity, nx is less than m. Thus, nx less than m less than ny, as we claimed. Finally, as n is in the natural numbers, n is bigger than 0. And so, you can take this inequality that we just proved and multiply everything by n inverse. As we claimed. And that completes the proof. Cool. So this is probably one of the longest videos that I will post ever. It's right now just over a half hour. So I hope you found it useful. I'll stop recording. See you in class. I don't know how to end these. Bye.